Today we're going to be learning about stoichiometry. This word can sound kind of confusing, but the point of this video is to make it seem actually kind of simple and to break it down, I guess, stoichiometry step by step. First, let's get a definition. It's the branch of chemistry dealing with relationships of combining elements, especially quantitatively. So basically, this is finding out if I have this number of grams of this molecule, how many grams of another product or reactant do I need in order for the product to take place? So let's go ahead and review balancing chemical equations really quickly. Our example that we'll use is carbon monoxide plus molecular oxygen yields, and then our product, CO2, or carbon dioxide. If you have already learned how to balance chemical equations, I encourage you to go ahead and pause the video and try to figure this out on your own. If you have not learned this yet, I want to encourage you to go ahead and watch my video on balancing chemical equations before we begin. So, excuse me. What we have over here is we have one carbon on our reactant side, and we also have one carbon on our product side. So those are balanced. And then our oxygens, we have one right here plus two oxygens over here. And then over here on our product side, we have two oxygens. So this would be three, that's two. We're not balanced there. So what we're going to do, let's try changing this to a 2, because if there's no number, if there's no coefficient, then we assume that it is a 1. So 2 CO2, these will change these numbers to now 2 carbons and 4 oxygens on our product side. So what can we do to go through and change this to make sure it's balanced? So we have 2 oxygens right here, and right here we only have 1. So what we need to do is we essentially, we also need to gain a carbon over here on our reactant side. So let's go ahead and write a 2 in here, and that should balance this out. 2 times 1 carbon is 2. Cross that out, that's no longer relevant. And then 2 times 1 oxygen would give us 2 oxygens right here, plus bring this down because it stays the same. We did not change that. And that will give us 2 plus 2 oxygens equals 4. We have 2 carbons on our product side, 2 carbons on our reactant side, 2 oxygens on our product side, and 2 oxygens on our reactant side. So our equation is now balanced. Now that our equation's balanced, and we reviewed how to balance chemical equations, let's go ahead and get into some stoichiometry. So typically with stoichiometry problems, they will ask you something like, if we have 56 grams of carbon monoxide, or CO, how many grams of oxygen, or molecular oxygen, O2, would we need in order to use up all of our carbon monoxide so that we don't have anything left over between the two of those? So here's how we go about this. We need to find two things. We need to find how many atomic mass units, or AMUs, are in carbon and are in oxygen. So the way we do that is we have our periodic table of elements. Let's go ahead and find our 2 elements. We have carbon, element number 6, which is 12, as you can see right here, 12 atomic mass units, and then oxygen, which is 16. So 12 and 16 atomic mass units. And we can put this table aside. There we go. So carbon equals 12 AMUs, and oxygen is 16 AMUs. So now that we know our atomic mass unit for our elements, we can start to figure this out. So let's figure out how many atomic mass units, or how many grams 1 mole of carbon monoxide would weigh. So let's forget about that too. Let's forget about this coefficient for now, and let's just figure out what carbon monoxide will weigh. So carbon monoxide is a carbon which weighs 12 atomic mass units, and then we have an oxygen which is 16. Let's add the two of these together, and we get 28. So we have 28 AMUs, or 28 grams per mole of carbon monoxide. So as we can see here, this is where we need to worry about our coefficients. We have 2 moles of carbon monoxide, and we have 1 mole of oxygen. So we know how many grams are in 1 mole of carbon monoxide. Let's go ahead and figure out how many grams are in 2 moles of carbon monoxide. So the way we do that is we just multiply our 1 mole times 2. So 28 times 2, you could use a calculator, or we could do this in our head, and it is 56 grams per 2 moles. So excellent. We have the atomic mass units, or the grams. We know how much 2 moles of carbon monoxide will weigh. It will weigh 56 grams. Perfect. So now we have, if we have 56 grams, then in order to balance this, how many grams of molecular oxygen would we need? So now our coefficient's just 1 of molecular oxygen. We only have 1 of those, and that's just O2. So what we would do, we have our oxygen, 16. We could do 16 times 2, or 16 plus 16, and that equals 32 grams, and that would end up being our answer. Let's try a little bit more complex of a stoichiometry problem. Let's begin with our chemical equation and balance it before we begin, just because it's good practice. So on our reactant side, we have 2 irons, 3 oxygens, and an aluminum. On our product side, we have 2 aluminums, 3 oxygens, and 1 iron. So the first thing that we could do is we could put a 2 right here. Now we have balanced our iron. We have 2 on the left side and then 2 on the right side. Our oxygens, on our left side we have 3. On our right side we also have 3, so that's good. We don't need to do anything to change that. For our aluminums, we have only 1 on our left side, while we have 2 on our right side. So we could add in A2 right there, and now we've balanced our aluminums. So now our equation's balanced. Let's go ahead and make this into a stoichiometry problem. So let's say we have 90 grams of our iron 3 oxide. How many grams of aluminum do we need in order to use up all of our iron 3 oxide in this equation? So I want to encourage you to try to figure this out on your own. Go ahead and pause the video and try to think through it. Okay, hopefully you had luck trying to figure this out, but let's go ahead and walk through it. We need to figure out our AMU, or how much our iron weighs, and then we need to figure out how much our oxygen weighs, and then also, aluminum. We need to figure out how much our aluminum weighs. So let's go ahead and get out our handy dandy periodic table. Where is it? There we go. So iron number 26 weighs 56 AMUs, excuse me, or 56 grams. Aluminum weighs 27, number 13, and then oxygen, as we know, weighs 16. So let's go ahead and write these down now that we know them. Iron was 56, oxygen is 16, and then aluminum was 27. Let me just double check that. Yep, 27. All right. So now that we have this information, let's go ahead and figure out how much does 1 mole, right up here, 1 mole of iron 3 oxide weigh exactly. So let's think about this. In every mole of iron 3 oxide, we have 2 irons. So that will be, which weighs 56, 2 of those. And then we have oxygen, which weighs 16, times 3. So let's go ahead and add this up. 56 times 2 is 112. And then 16 times 3 for our oxygens is 48. Add those together, and that gives us 160 grams per mole of our iron 3 oxide. So now that we know how much it weighs per mole, we now know, we didn't do this in the last example, that we have 90 grams of it. In the last example, it just so happened that we had exactly, the weight that we had was exactly 2 moles. So now we need to figure out how many moles is 90 grams. So the way that we can figure this out is by doing 90 divided by 160, and that gives us 0.56. So we have 0.56 moles of iron 3 oxide. So what these numbers, these coefficients, what they tell us is for every 1 mole of iron 3 oxide we need to have 2 moles, oh, there we go, of aluminum. So if we have 0.56 moles of iron 3 oxide, that means that we need to double that. 0.56 times 2, and that gives us 1.12 moles of aluminum is what we need to figure out. So simple enough. We know our aluminum weighs 27 grams. 27 grams. And we need to find, it is in what 27 grams represents 1 mole. So we need to figure out 1.12 moles. So all we do is just multiply 27 times 1.12, and that gives us the answer of 30.24. And that will be our answer. So if we have 90 grams of iron 3 oxide, we would need 30.24 grams of aluminum in order to use up all of our iron 3 oxide. And we're done.